Thank you very much for the introduction. You guys understand that whatever we do, our pedagogical issues may not be exciting as technical. And the path that leads to our solutions is actually mostly about small changes that we make in our teaching methods and in our curriculum. Consequently, I decided to start with something that I think it's very exciting, and it is actually a technical simulation that you see right here in front of you. This is a typical jet engine dual stream nozzle, and what you're seeing is some nice duct modes. And I think, Nagi, you will appreciate this. It was this morning at your acoustical presentation. So yeah, it was a wonderful thing to see something in front of your eyes that you couldn't otherwise see. So what you're looking right now is the origin of how this research started. It started last year in collaboration with the NASA Glenn Research Center colleagues. In specific, I was collaborating with two branches, nozzle and inlet branch and acoustic branch on the top of that. Our initial approach was experimental approach, and you see NASA GRC, a large dome, large scale experiment, and you catch some persistent tones. Then maybe you want to scale down the whole model, and what you're seeing here is actually a scale down model, and I hope that I can catch it here, right? So this is scale down 50% model, and again, these tones are very, very persistent. So maybe what you want to do is you want to simulate things so that you can visualize a few items that you cannot otherwise get from all these experiments. So what you're seeing right now is actually a center body of two different nozzles. You see a 4-strut nozzle and you see a 3-strut nozzle. 3 and 4 struts are there. They're starting from the center body and going outwards as a support. And what we were trying to do is the simulate experiment, see can we get the same tones or not, and what is actually causing them, the physical background. So yes, at this point, everybody can start wondering, what am I talking about? Hisses and howls in nozzle and nothing about stem. So this is where stem part kicks in. So what you're seeing here is actually an application from my students that was funded by Connecticut Space Grant. And it was not only the application that my students built, but they also built some parts of the simulation behind it. So maybe you want to get to know some of my students, and I hope that you can hear me now too. So this is Jeffrey Severino, and Jeffrey was so excited about the whole project that he actually decided to 3D print a bunch of nozzles, even though we didn't need them at all. Never mind, but on the top of that, he got himself excited and psyched up about NASA and the research. So guess what? He ended up applying. I was his supporting professor, and he ended up whole summer at NASA Glenn GRC, and his NASA mentor wrote me a 2-page email at the end of the summer in August, saying that she could not have wished a better student and better help with her research at NASA. So this is just one example what we can do in the classroom, and the other example is shown right here. This is Lena Dubiel. Lena is not only junior Regent recipient, but she also has undergone 3 of my courses with 30 simulations that were embedded in them. Yeah, that's really not that easy. This summer, she volunteered to work on United Technologies Research Center project, and that project is about the numerical calibration of a COBRA probe, and she's currently applying for the support of NASA Connecticut Space Grant. So now, going all the way back to our original STEM question, how to embed simulations and how to enhance research component in our undergraduate curricula. It's really not an easy topic, and I struggled with it for many years before finding the solutions that I will currently talk about. So yes, this is engineering curriculum in all our schools. Throughout the nation now, we have problem and project-based courses. They start on a freshman level, and then we move on students to the 2nd and 3rd year to the capstone project. Yes, they do have lots of lab experience, and they do have lots of hands-on experience, but in my opinion, it was not enough. I used to be a chair of a department for 8 years, and whenever we had a department meeting or a meeting with the board of visitors, there was a big discussion of what to do with simulations. Is this all pretty pictures? Can we have something meaningful on the undergraduate level? And we couldn't solve that problem for many, many years. So I'm returning back to the research component from time to time. I will call it inquiry-based learning, because we all know that the research, that students can do, of course, it's a limited in range. So that's why I'm swinging between research and IBL expression. So what you're seeing here is just a very visual example of lab that used to be a storage space before I got hold of it, and I employed 20 students, graduate and undergraduate, so that now we can have a turbomachinery research lab with 2 wind tunnels and a water table. But here is the problem. We are doing this on extracurricular basis, and this research is hands-on, and who is doing it? Mostly people that are highly interested, highly motivated, our best students, and you see some of them right here. So of course we have to do this because it has tremendous benefits. Our students have to develop their skills, and this all underlines our basic design activity. So another illustration that can nicely slide into the simulation part is the illustration of what my students can do, say, in a water table. We put in the test section that we obtained from Pratt & Whitney. This is a linear array of the blades, and we're trying to visualize secondary flows. So you see these vertical patterns. Yes, these are secondary flows that both graduate and undergraduate students can visualize in our lab. Well, again, that leads me back to the problem. We want more simulations and more research, and we want to cover all our students. So how do you cover whole student body? And that was the biggest issue. Initially, what you try to do is you try to reproduce some sort of research experience in an extra course that is a professional elective graduate level course. And what you're seeing here is some work from my graduate students in a multiphysics course that Professor Epps and we started about probably 10 years ago. And throughout experiences with that course and our students, we realized, okay, our undergraduate students actually can volunteer and can take this as a professional elective, and this is great, but they are doing it in a senior year. Well, maybe senior year is already too late. So this is a nice example of a lady, Karen Brzezowski, that is one of our first students, and this is her project. She got funded again by a NASA space grant with a very nice undergraduate fellowship. But this is really not what we were after. We were after undergraduate curriculum, and now the question becomes where and how. So probably most of you will recognize Otto Lilienthal. Otto Lilienthal had about the first flying man, so to speak, 2,000 glides, right, and 5 hours of time spent in flight. But remember how he ended up? With a broken neck. So there I go back to my classroom. I don't want to break my students or myself in the classroom. And what I want to do is I want to have a nice experience in my thermofluid sequence. So I start with fluids in the fall, and I end up in heat transfer in spring. So how to do it in a way that wouldn't hurt my actual class time. So yes, these are my teaching and learning challenges. Sometimes I like to call this millennial problems, not millennium problems. Yeah, you presented just one equation. I promise this would be my one and only equation, because it's a very hard on us. It's hard on students. They're hands-on folks, and they want to do something exciting. What they don't understand at that stage, that what is exciting is actually math, because it is underlining all our efforts. So what do you do? On undergraduate level, you are teaching a survey course. And what are the challenges of a survey course? Well, I have to deliver quite a lot of fundamental material, and I have to teach students fundamental problem-solving techniques. So This is my 3-body problem. Whoever likes sci-fi may remember that there is a 3-body problem book too, and Newton's 3-body problem. There would be also a ball lightning book from the same author that you may want to read. It is published just a month ago. So going back to my 3-body problem, it is a coverage of the required material. Why do I say coverage? Because there's a certain breadth and depth that I have to hold on to, and I have to deliver in a short period of time, and I must not change that. So what I did, my brilliant idea was maybe to use simulations. My second problem is consistent use of immersive and exciting visuals. Okay, I'm using simulations. And finally, how to integrate meaningfully mathematical and numerical simulation, mathematical concepts that underline simulations and simulations themselves. So this is the 3-body problem that I'm solving. And I'm presenting a very, very simple solution. It's nothing life-threatening, as you guys talked before, but I think it really helps in the classroom. So what I did is I took my simulation application building and I shoved it outside of the classroom. I don't talk in my classroom about simulation and apps. What my students have to do, they have to do it outside of the classroom, and this is their new homework. I have scaffolded and contextualized simulations labeled as a homework. Their old homework, guess what? It still exists. Now it is called practice problems, and it is part of a necessary preparation of the exam. If they don't do it on their own, they will not pass my exams, but I'm not grading these homework problems. So yeah, maybe you didn't notice, but I was sneaky. I piled lots of work on them. So they have to do both simulations, applications, and they have to practice on their own. So basically, what I'm also doing is I'm trying to embed inquiry-based learning or a little research in a context of 3-credit lecture course. And yeah, all that is very hard to do and took me some time to figure it out. So I will share my strategy with you. It may or may not be helpful, but it's nice to know. So what you're looking at is a snapshot from my course management software. It's a Blackboard, and I want to give you some background on where I come from. Well, my accent comes from Belgrade, Serbia. This University of Hartford provides me my professional surroundings. And just last year in a Business Insider, you wouldn't believe, but we were among 27 colleges where engineering students go to earn the most money. Yes, 27 colleges, and we were on the 14th place. We tied with MIT and Cooper Union. I believe there was 2 more. One of them was Tufts. So if you take a look, and hopefully you can see the numbers, mid-career median pay for our students is $130K. But we are a liberal arts institution, so basically our students pay hefty price. We have to justify that price, and we have to be very current in our delivery. So here is my strategy. It has 4 different steps that can be broadly represented as follows. First one are, of course, immersive and exciting visuals. So what you're seeing here is, again, snapshot from my Blackboard course management system. It is, of course, online, but in the classroom, I go ahead and I'm using the simulations and apps as a way of my visual delivery. So what you're seeing here, if you take a look somewhere on the side, and you may have noticed, so this is the name of the course, this is fluid mechanics course, but I have something similar for every single course, and this is an example of the heat transfer. So these visuals are applicable both in the classroom and outside of the classroom. And what do we do outside of the classroom? Well, in the first week, I start, say, heat transfer, and you also want to talk about the heat transfer modes. You start with simple 2-dimensional conduction, and you want to talk a little bit about boundary conditions. So you will all probably recognize the basic module from COMSOL that is a 2D conduction that my students work on in the very first week. Marching through the semester, they will encounter unpleasant things such as a cylindrical coordinate system, but while doing it using these simulations, I think they are surviving it quite well. By the time we come to the 5th week and the 5th chapter, which is on transient conduction, they're able to understand both the physics that is behind any project that they're doing, and they are able to build apps. So moving forward, it's much more fun because now we can talk about some practical stuff. And as you can see, these are examples of 2 different heat sinks that we do both in the classroom and outside of the classroom. So second strategy must be, at least in my opinion, enhanced online environment, because most of the time when we are using these learning management systems, we just tend to upload PDFs and whatnot. So I think if you make it more exciting, then you will deliver more outside of the classroom and you will have less load on you during your office hours. So what you're seeing here, just some elements of my enhanced online environment in which I heavily rely on multiple things. So what you're seeing here is maybe I find an app server from Europe. I believe this one was from Europe that may be useful for my students. I can find many nice things on COMSOL blog, and I cannot thank you enough for a great blog that is both exciting and technical. And I also heavily use YouTube with most wonderful visual materials. I mentioned that my simulations are new homework. So what you're seeing here is what I'm delivering online. Students are going online to find their little projects. And at the beginning, of course, they will be very, very simple. So I start with simple 2D conduction, and I'm providing my own grading criteria. I don't even like to use the word assessment. So having said that, if you take a look at the criteria, you may be too far to see it. But at the bottom of that criteria, I have an extra section, and that extra section is inquiry-based learning or a research. At the beginning, it is really very simple, and it is mostly about getting to know your software without using canned instructions. So what I'm asking them, hey, go ahead and do the cut plane or cut line or whatever, without the help of the instruction. You have to look for it on your own. But later on, it becomes a little bit more demanding and a little bit more tied with the actual physics of heat transfer or fluid flow, depending on whatever I'm teaching. So final course strategy is the research. Well, how do I embed it in research and how do I ramp it up? So this is just an example, and it's really very simple example. We are all familiar with the coefficient of the drag curve for the sphere and the smooth cylinder. So many years ago, when I was getting started with teaching, I used the materials from all over the place. So you see here a patchwork of different visuals that will help my students understand, how to use this curve and what is behind it and what not. So now it looks much more uniform, because now I can have an app and work an app and have some sort of understanding. This is what you get for different Reynolds number. This is a very nice example because it starts us with the flow separation, vertical flows, and many other exciting things. So as a part of my course, students in fluid mechanics do the canned simulation first of a flow past the cylinder. And then immediately after that, I'm asking them, hey guys, can you make an app? And Lena indeed last fall made an app, and it is very clear in their instructions that they have to deal with a non-engineering user. So, they have to make that app understandable for non-engineers, for potential use outside of their class. Well, how does this tie with whatever I talked at the very beginning? At the very beginning, I talked about undergraduate research. So you see Jeffrey and you see Elena, both of them have undergone a set of extensive simulation and application building exercises, and they came up with a wonderful app that you're seeing right now. Well, what are the benefits? The benefits to students are apparent because they hone their skills and they have valuable skill on their resume. But on the top of that, it's a great PR for my university, which is a liberal arts university, and it is a great vehicle for my students. Last spring, I used these two to showcase applications on engineering.com. And now, if anybody's interested, they can take a look at what they did, and it's still online, both on COMSOL.com and engineering.com. Interestingly enough, how we all full closed loop, coming back to the beginning of our computational aeroacoustics. So take a look what we have here. What they do in the classroom, flow over cylinder. And when Jeffrey and Lena started exploring the flow in our two-stream nozzles, we realized actually that these peculiar tones we mentioned at the very beginning, where do they come from? Well, this is flow separation at the struts, and you currently, hopefully, are able to see these 4 struts at the back end. Well, everything ties together, our teaching methods and our final outcomes. I just want to feature Stefan Kalik. Dr. Tom Epps, my colleague from University of Hartford, just delivered his paper this afternoon. So yes, your students will be able, hopefully, after a set of relatively simple exercises, to do something that is meaningful for them and for all of us. In conclusion, what I try to present here is a case study in a course design. And my objectives were to better illustrate thermofluid concepts, to excite my students about all the research and the beauty of thermofluids, to embed deliberately simulations and application building because it is a great skill for them, to facilitate research, to help students and myself to combine project-based, problem-based learning with inquiry-based learning. And now I'm blanketing all of my students. I'm not just working with 1 or 2 of most talented, but all of them in my class have to do it. So I would like to thank you all for your patience. Thank you.